All right, everyone. So this is 322, and this is focusing on types of orbits and orbital mechanics and a brief introduction to those. You can thank Josh for all of your extra videos and graphics that he has added to this presentation for you. So first of all, here's a table of contents. All of these slides are linked. There is a fair amount of stuff inside of here. Basically, the big concept that we were looking at is what is an orbit, what shape is an orbit, how do we label the parts of an orbit, and then more importantly, how do we calculate orbits? So that's where we are headed. So first, let's take a look at what is an orbit. So an orbit is a closed path around which a planet or satellite travels. Remember, satellites can be human-made or they can be naturally occurring. So Johannes Kepler discovered in the 1600s that planets orbit in an elliptical pattern and not a circular pattern. And satellites, either natural or human-made, do orbit Earth as an ellipse. Now, elliptical orbits remain fixed in space, and the Earth spins under a fixed satellite orbit. So basically, we have things that go around the Earth, and then the Earth goes around the sun. So we have a lot of kind of spinning and orbity stuff going on within our solar system. So most of you have had geometry, so let's talk about what an ellipse is before we continue. So an ellipse is a two-dimensional shape that's produced by a plane fully intersecting a cone. Note that a plane intersecting the cone at an angle perpendicular to the cone center line will form a special ellipse called a circle. So let's get more into the nitty gritty when we look at a circle. Circle is a set of points that are fixed around a constant distance from a center point or the focus. So right here you can see we have a circle, center point, and all of these points are equidistant. An ellipse is different because we have two foci instead of a center. So we have a foci here and here as well as our center point. So the sum of distances from the foci are constant. So a plus b is our constant. So the distance here and the distance to here are constant. So a circle is simply an ellipse with both of the foci located at the same point. So that is in the center. Satellites orbit the Earth with one focus at the Earth's center, and the other focus is an empty point. Now that can be within the Earth's boundaries, but it may not be. Again, remember, we are orbiting on an elliptical pattern. So more importantly, when we look at an ellipse, we have a few things that we need to define. A is defined as half of the major axis, and then B is defined as half of the minor axis, and then C is the distance from the center to either the focal point. And then of course, circle is A and B equals the radius. Now there's more information about what we use these calculations for and the foci of an ellipse in this great video that Josh added to your presentation, which you can then view once these slides are linked into my MCPS classroom. So in your notes, I do want you to draw this diagram of an ellipse and label the parts. So this is an ellipse, obviously. Okay, and then you'll notice that the ellipse is divided by two dotted lines. One is referred to as the minor axis, so that is the shorter side, and then we have the major axis. The minor and major axis are split in half by the center. We then have foci on the major axis, and then at the ends of the major axis, we have what we refer to as the vertex. On the edges of the minor axis, we have what we refer to as the covertex. Now, looking at this slide, this might be your first glimpse at a somewhat 3D representation of orbits. Typically for this unit, we are in a software called STK, and we're actually able to rotate around bodies in a simulation to see various orbits and what they look like. So this is kind of the flattened screenshot from STK, but it does give you kind of that 3D feel of Earth. And then you'll notice that we have a really tight orbit right here. We have a slightly larger one across here. We have one that comes out in this direction, and then we have the horizontal one here. So this is just an example of the different size and angles we can have of orbits for things that are circling our planet. So again, this is another example of those same orbits. This time they are labeled by their type. So each of these acronyms stand for a different type of orbit. So LEO is low Earth orbit, and then HEO, if you guessed, is high Earth orbit, and then GEO actually stands for geosynchronous. So these are just the different types of orbits that we can have. We can also have polar orbits, which is probably what this white line is representing, because they go around the poles as they orbit. So how are orbits described? Well, orbits are described by a set of parameters called orbital elements, or Keplerian elements. So the Keplerian elements are a set of consistent of 6 parameters plus a timestamp. 2 of the elements or parameters describe the size and shape of the orbit. 3 of them describe the orientation of the orbit in space, and then 1 describes the location of the satellite within the orbit. So another element that we need to look at is eccentricity. So eccentricity describes the roundness of an ellipse. So the closer it gets to a circle, the more that just describes the eccentricity. So we can calculate eccentricity with this formula here. Please jot that down in your notes. And you'll notice that this is referring to a squared and b squared. A and b are referring to the major and minor axes of the ellipse. So we visited that in that video, and I gave you those variable titles and explained what they were on a previous slide. So if you didn't get those, just rewind the video real quick and make sure those are in your notes. Okay, so continuing with eccentricity, this value is between 0 and 1 for closed orbits. And eccentricity of 0 means the orbit is actually circular. And an eccentricity of 1 or greater means that the orbit is not closed. So this would be used for interplanetary missions. So satellites in these types of orbits do not come back to their original starting point. That's why it would be an open orbit. So if we were sending a rover to Mars and we did not intend for the rover to return to Earth. So orbits may have the same eccentricity, but they actually can also be different sizes. So in this instance, in this graphic, these 2 orbits have the same eccentricity, but they are obviously very drastically different in terms of size. So that means that there has to be other Keplerian elements which describe the size of these orbits. So this is where we start talking about the axis. So the semi-major axis describes the size of the ellipse, and it is half of the largest diameter, which is the major axis of the orbit. So if we have the semi-major axis from the center of the ellipse to the edge versus our major axis, which is 2a, which is the entire distance across the longest portion of the ellipse. Okay, just a few more vocab words that I want to put out to you guys. First, we need to look at the apogee, and the apogee defines the point in orbit that is farthest from the Earth. So in this graphic over here, we have Earth. This point right here is our apogee. Now, the inverse of that is essentially perigee, which is the point in an orbit that is closest to Earth. So on the back side of this is our perigee. This is where our satellite is closest to Earth. The apogee altitude is the distance between the surface of the Earth and the apogee, and then the apogee. So that would mean how high we are in the sky when we are at the point of apogee. And then we have the perigee altitude, which is the distance between the surface of the Earth and perigee. So again, that would be the altitude that we have when our satellite is at perigee. So perfectly circular orbits don't have apogee or perigee. So those remain undefined. If we have a perfectly circular orbit, then there is no apogee or perigee because everything is equidistant from the center. So realistically though, perfectly circular orbits can't be achieved. It's just not feasible. Generally, circular orbits are described by their altitude, and the semi-major axis rarely is used to describe circular orbits. So for a circular orbit so something that is really, really, really close to a circular orbit, we're not going to have apogee or perigee, and we simply describe them with their altitude. Now, if we need to calculate the altitude for those circular orbits, we do have a formula that does that, okay? So what we're looking at here is T being the orbital period, and then A is our semi-major axis, which is right here and right here. And then we have mu, which is our gravitational parameter. That would be a constant that we would have to pull. And then G is a universal gravitational constant right here. Okay, so there's our gravity. And then we have mass, which is the mass of this central body. So this actually gets translated as Kepler's third law. So that means that the square of the period of a planet is proportional to the cube of its mean distance from the sun. So what does that mean? That sounds super complicated. basically what we're saying with this formula is the period of a planet, okay, so the time it takes for it to loop around an orbital body, is proportional to the cube of its mean distance from the sun. So if we were calculating the altitude of Earth, we could take its mean distance from the sun and cube it, and that would mean, and our period, so the time it takes us to get around the sun, 365 days, is proportional to that mean distance of the sun. So it's stating that there is a relationship between those things.